In our previous video, we discussed Ernst Schrödinger and his contribution to the understanding of the organization or structure of electrons. Now, what he created was a series of wave functions that described the probable location of electrons on each of the energy levels that Niels Bohr was able to mathematically show existed within an atom. Now, the answers to the wave function is a set of locations. Now, these were basically a graph, a scatter plot, if you will, of points. However, these were three-dimensional points that were plotted, if you will, about a three-dimensional axis. Okay, so this would be the x-axis, and this would be the y-axis, and this is the z-axis, okay? And the answers to the wave function were in actual points that were plotted, okay, around this axis, and the center here, the origin, if you will, would be the location of the nucleus. Now, interestingly enough, okay, at each energy level, Schrödinger was able to demonstrate that there were specific different sets of answers depending on the energy level. Okay? And they actually defined, very interestingly, three-dimensional shapes. Schrödinger called these shapes orbitals because they were not circular orbits, so he didn't want to call them orbits. Okay? And what they are 3D locations around the nucleus which were highly likely to contain electrons. These different possible shapes at each of the energy levels, he called these sub-levels, and he was able to demonstrate that these were where the different lines in the atomic emission spectra came from. Now, you'll recall that hydrogen has a very specific set of lines that correspond to the 7 energy levels, okay? And there's only one electron in a hydrogen atom. However, as more and more electrons are placed into a particular atom, there have to be more and more places on these energy levels to hold the electrons. And these sub-levels had slightly varying amounts of energy on each energy level. So that's the reason why we see multiple colors or wavelengths, different patterns. It depends on where they're arranged in the ground state and where they can end up moving to as they absorb quanta of energy. Now, each of the orbitals have a very unique and interesting looking shapes. Okay, the orbitals are named according to a letter designation. The first letter, the first type or shape of orbital is the letter S. Okay, and S stands for sphere, and that's exactly what they're shaped like. They're round like a ball. That would be the nucleus in the center, and they are capable of holding a maximum of 2 electrons. And there's one of these on each energy level. Okay, and they're stacked inside each other. Okay, so the orbital on the first energy level is small, and then the orbital on the second energy level is shaped the same. It's a little bit bigger, and then the next one is a little bit bigger, and the next one is bigger than that. It's a little bit like the Russian nesting dolls that you see, where you take off the big one and there's one inside that's the same shape but a little smaller, and then you go down and the next one's a little smaller, and so on and so forth. So they get smaller and smaller and smaller. Okay, so the 1s orbital is the smallest one. The next shape The next orbital type of shape is P. P stands for propeller. Because this is roughly the shape. Okay? Again, the nucleus is here in the center, and they'd be shaped like they're kind of like two balloons that are held together at the center. Now, there are these come in a set of 3. Okay, one of these is on the x-axis, one of these on the y-axis, and one of these is on the z-axis. Okay, so we have a total of 3 of them, two electrons each. So that means that they can hold 6 electrons total. Now, there's one of these on each energy level, but these begin on 2. In other words, there is no p orbitals on the first energy level. The next energy level type is the d orbitals. I'll call these the double propeller and the donut. So what are these shaped like? Well, there's 4 of them that are shaped like this. Okay? However, they're just turned in different directions. One of them is shaped like this. It looks like one of the p orbitals, but it has like a donut or a ring around the middle. So there are 2 electrons in each of these orbitals. There's 4 shaped like this and 1 shaped like this. That means that a set can hold 10 electrons total. And there's 1 on each level. Beginning on level 3. Okay, the next last type are the f orbitals. And I call these the funny shapes in the flowers. Okay. These are names that I made up that go along with the letter designations. It helps you remember, when you look at the letter F, it helps you remember what they look like, what the shape is. Okay, now these are call these the flower shapes because these have 8 lobes. You notice the pattern here. 2, 4, 8. So go up here. Okay. So there are 4 of this shape. Okay, and each of them are just kind of turned slightly in different directions. Again, the nucleus is in the center. Okay, and then the last 3 are kind of shaped like this. There's 3 of these. They kind of look like mice or something kind of pointing at each other. So there's 2 electrons in each of these. So that means you got 7 total. 14 electrons total. Okay, and you can see the pattern. Okay, electron configuration is all about patterns. And these are on level 4. Okay, so if we look at level 1, okay, this would be equivalent to an S set. So there's 2 electrons total. On level 2, there's another S and a P. Okay, remember, the S can hold 2, the P can hold 6, so there's 8 electrons total. On level 3, there's S and P and D. So we've got 2, 6, 10. So the 18 electrons possible on level 3. So this is kind of unusual and strange, but this is exactly where the electrons happen to be located. And so if we take a look now at our periodic table, we will discover that there is specifically a relationship between all this orbitals and how many electrons are on each level and everything, and the organization of the periodic table. So if you get your periodic table out, we're going to take a look at it, see if you can locate the pattern, because we need to understand the patterns in order to do what is called electron configuration. Okay, so here's our periodic table. And remember, we said that level 1 holds 2 electrons, level 2 holds 8, level 3 holds 18, and so on and so forth. Okay, now first of all, we know that there are 7 energy levels, okay, main levels where electrons can be located. Now if you look at your periodic table very carefully, you'll notice that there are 1, 2, 3, 4, 5, 6, 7 rows or periods. I'm going to erase this for a second. I'll move this out here. Hopefully you can see okay. But I'm basically numbering the rows, because each of these rows corresponds to one of the 7 energy levels. So that means that elements on this level, all of their electrons are on level 1. Elements on this row, their electrons are in level 1 and level 2. All the elements that are in the third row, their electrons are on level 1 and 2 and 3. Now, that's one pattern. The second pattern is, remember we said that s orbitals have a maximum of 2 electrons. If you look carefully, there's these 2 columns on the periodic table over here. We said that p orbitals, there were always a set of 3 with a maximum of 6. So that would be, if you look over here, look at the columns over here, we've got 1, 2, 3, 4, 5, 6. Now the d orbitals, there's 5 of them. Each of them can hold 2 electrons for a total of 10. And look here in this middle section here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what we see here is that the periodic table can be divided up into some major sections, and each of these sections corresponds to a certain type of orbital on the periodic table. This here is called the S block, these 2 rows. These rows over here, excuse me, these columns, are called the p block. These columns here in the center are the d block. Okay, so elements that are here, their final electrons are located in the s block. Elements that are here, their final electrons are in the p block. And elements here, their final electrons are in the d block. So where's the f block? Right down here. Okay, so this, make sure that you have written all of this information in on your periodic table. There's room in the margins for you to number the rows, and you should level S, P, D, and F on your periodic table. Now, one of the worksheets you're going to do uses something called orbital diagrams, which is another visual way of representing how the electrons fill in the orbitals on each of the different energy levels. Okay, what you'll focus on for your test is writing out not the orbital diagrams, but writing out electron configuration. Now, electron configuration is simply a listing, if you will, of all the electrons in a particular element, and it shows what energy level those electrons are on, which orbital type they're in, and how many are in each of the different orbitals. Now, we use our periodic table to actually do this. Okay, so we're going to start here with hydrogen. I'm going to make a little bit more room down here. Okay, and we're going to write out the electron configuration for hydrogen. Now, when we do this, we start out by listing what energy level hydrogen is on. So the energy level is on row 1, so it's on energy level 1. Then we say, okay, where are hydrogen's electrons? Well, hydrogen is in the s block on the first row, so that means that all of its electrons are in the 1s orbital. And how many electrons are in that 1s orbital? Well, hydrogen has 1 electron, so that 1 electron is in the s orbital, so we're going to write 1s1. Okay, what about helium? Well, helium has 2 electrons. Now, helium is an interesting case. Helium is written over here because it's part of the noble gases. However, helium is on row 1, and the only orbital type that exists on energy level 1 is the s orbital. Excuse me. So that means for electron configuration, helium is actually more appropriately placed in this empty looking position. So I'm going to draw it in because for electron configuration, this is the element. Helium actually sits on top of the alkali earth metal family. Okay, for everything else, helium belongs in its normal position. It is indeed a member of this family, okay, but it is actually part of, sits on the alkali earth metal family for electron configuration. Okay, so let's scroll back down here. What is helium's electron configuration? Well, it's on row 1 again. It's still part of the s block because we now moved it. It's the second element in the s block, okay, which means that it has 2 electrons in the s block. Okay, we're going to extend this pattern. Let's look at lithium. Now, lithium is on row 2. This means that it has electrons in 1 and 2. Now, row 1 is just the 1s orbital, and it has room for 2 electrons, so lithium's 3 electrons the first two of them have to be in the 1s orbital. So it's 1s, 2. However, lithium is on the second row, which means it also has electrons on level 2. Hey, lithium is located in the s block, meaning that its electron is in the 2s orbital. And since lithium is the first element in this position, that means it has one electron in the 2s orbital. Now, to make a long story short, when we write electron configuration for an element, we simply walk across the periodic table. We always have to start in the upper right-hand corner because we're always going to fill in the 1s orbital, and then we're going to move left to right and go down the table, and we show how the electrons fill in the additional orbitals. So now we're going to jump to carbon. I'm going to draw this one right here so that I don't have to slide up and down. Okay, carbon is here. So again, we're going to start here at the beginning. So we're going to start with row 1 always. We're going to start with the s block. And I'm going to say, okay, we're going to fill up these. We've got 2 elements here, so we're going to fill up the 1s orbital. Now we go to row 2. This is the 2s block. Okay, there are 2 elements. That means we're filling in 2 more electrons. Remember, the 2s can only hold 2 electrons, and then it has to be, it's filled up. You got to move to the next one. Okay, now we're going to go, we're still on row 2, but now we've entered the 2p orbital. Carbon is in the second position, meaning that carbon's last 2 electrons are filled into p orbitals. 1s2, 2s2, 2p2. So 2, 2, and 2. Okay, so before we go any farther and practice any more of these, we're going to make a notation that there are some rules that govern electron configuration. Okay, the first rule is called the Aufbau principle. The Aufbau principle, the word Aufbau is a German word that means build up. It means that electrons fill the lowest energy orbitals first. Okay, build up. So you start with the lower energy orbital, you completely fill it up. Then you move to the next lower energy orbital and you completely fill it up, and so on and so forth. The next one is called the Pauli exclusion principle. Okay, this basically says that one orbital can hold a maximum of 2 electrons. Now the reason you can fit 6 orbitals in p is because it's a set of 3, each orbital with a maximum of 2. The third one pertains mostly to the orbital diagrams that you'll learn how to do. That's Hund's rule. That says for a set of orbitals like p, d, and f, each orbital gets 1 electron before pairs are made. Okay, it's a little bit like the like when you're dealing out a deck of cards if you're going to play a game. Okay, you go around, you give every person at the table one card, and then you go around again and you give them all a second card. Okay, so if we use, for example, this is a set of p orbitals. Okay, and this is what we call the orbital diagrams. Okay, if we're going to make a line, sometimes you'll see boxes. Okay, and this would be the p that's on the x-axis, this would be p on the y-axis, would be the p on the z-axis. Okay, that means if I fill them in with electrons, I'm going to use arrows to represent the electrons. Okay, so if I have 3 electrons going into a set of p orbitals, there'd be 1 in the first orbital, 1 in the second orbital, and then 1 in the third orbital. So I don't put 2 and then 1. I put 1, 1, 1. Now if I had 4 or 5 electrons, so if I had 4, I would fill in this one. If I had 5, I would fill in this one. Okay, the electrons point, the arrows go up and down. So these are the ones that are filled in first, and these are the ones that are filled in second. Okay, so we're going to go back up to our little picture here. Okay, and now we're going to practice. I'm going to erase this. We're going to do another electron configuration. We're going to do aluminum. Okay, now remember, you're going to start at the beginning and you're going to just walk across the periodic table. You'll write down what orbitals are getting filled up as you go. Okay, so this is level starting here. So we'll fill in 1s2 first. Okay, then we go to level 2, second row. We're going to fill in the s orbital first. 2 elements, 2 electrons. Okay, now we're going to go to 2p over here. Okay, we're going to fill the p up all the way because we're going to get down to aluminum. So that's 1, 2, 3, 4, 5, 6. That means we're going to put 6 electrons in the p. Now we go here. Oh, now we're in row 3. Okay, it means that we're now filling in electrons in level 3. Okay, this is, so we're back to S. Okay, so we start a row in S. 3s. 2 elements means we're going to drop off 2 electrons here. Okay, and now we get here, we go into 3p. Aluminum is in the first position in the p block, so there's 6 positions. That means the last electron is in 3p1. Start to see the pattern? Okay, so this is what is called longhand configuration. It's called longhand because it is a bit long. And as you can see, as you go farther and farther down the periodic table, it gets longer and longer and longer. Now, before we go in further, we need to talk about what happens right here. Remember we talked about how the third level can hold a maximum of 18 electrons? However, if you look across here, okay, there's only 10 electrons here. So where's the other 8? Excuse me, so there's only 8 electrons on this row. Where's the other 10? They're right here. Because of the Aufbau principle, there's a little quirk that says that s orbitals are very, very, very low energy. So when the orbitals are getting filled up, the 3s on level 3 gets filled up, the 3p gets filled up, you would think that 3d would come next. However, 4s orbital actually has a little bit lower energy than the 3d orbital. So the 4s gets filled up before 3d. So on your periodic table, you need to renumber this section, these rows in the D blocks. You need to put a 3 in between calcium and scandium, a 4 in between strontium and yttrium, a 5 in between barium and lanthanum. You've got a little star on your periodic table, and a 6 in between radium and actinium, which is also a star on your periodic table. You guys have cadmium and rutherfordium, and these are actually shifted down, which is fine. Okay, so when you get back over here, then you need to go back up to 4. So if you look at it, the orbital that the order in which orbitals are filled in is 1s, 2s, 2p, 3s, 3p, 4s, then 3d, then 4p. then 5s, then 4d, then 5p. Now, when you get down here, your periodic table has little stars here. Notice the jump in atomic numbers, 57 to 72. Where's the missing elements? They're right here. So this means that these elements get inserted in here. However, remember that F's appear for the first time on level 4. So you got another weird out of order shift on the periodic table because F orbitals are super high energy orbitals. So the 4F orbital, even though it's on energy level 4, is really super high energy. So that means that you're going to put a bunch of, you're even going to fill up the 5S and the 5P and the 6S before you put a single electron into 4F. Now, I call this the detour on the periodic table. So when we are doing a long configuration, anything past barium, you have to remember that when you leave here, you don't go directly to 5D. You have to drop down and do the 4F first. And then if you do an element past lutetium, you have to come back. Okay, so let's do a couple of examples of that. Okay, so let's do mercury, Hg. Okay, so remember, we're going to start at the very, very beginning. So we start with 1s, and we go across those two elements, s2. Then we go to 2s. We're going to cover those two electrons, 2s2. Then we go to 2p. And that's 1, 2, 3, 4, 5, 6. Then we go to level 3 now, so we go to 3s. We go 1, 2, 3s2. We go all the way across here. Now we're at 3p. We're going to go all the way across 1, 2, 3, 4, 5, 6, 3p6. Okay, now we're going to 4s2. Okay, now we're going to 3D, and it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to get across. That's 3D10. Yeah, this one's getting long. Okay, then 4P, 1, 2, 3, 4, 5, 6, 4P6. Okay, we made it all the way to here. Okay, next row is 5. Now we're back in the S block, 5S2. And then we go to 4D10. And then we're here at 5. And we're back to P. And we need to go all the way across, so that's 5P6. Okay, almost there. Row 6, back to the S block. 2 more here, so 6S2. Go down a little bit. Okay, now, we can't go directly to 5D. We got to drop down here and do these first. So we have to do the 4F, and it's 14 all the way across. 4F, 14. Now I go back and I do the 5D. Mercury's all the way at the end of the 5D section. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 5D10. Okay, that's long, but you'll get lots and lots of good practice. Okay, now, there is a shorter way of doing this. It's called shorthand. Shorthand configuration begins with a noble gas. Okay, even though the noble gas is right. Okay, so the last column on the right on the periodic table. So we're going to place the symbol for the noble gas in brackets. And then we're going to add the normal configuration from the noble gas we chose to the element. Okay, so let's take a look at that. Okay, let's say I want to do the shorthand configuration. Here, I'm going to erase this. For the element cobalt, which is shorthand. Okay, so I'm going to do cobalt in shorthand. Now, which noble gas do I pick? I have to pick one of these. Well, what you do is you pick the noble gas at the end of the row above your element. So cobalt's my element I'm going to write. I go one element, one row above, and argon's at the end. So I will put the symbol for argon, AR, and I will put it inside a pair of square brackets like that. Then I'm going to write the normal configuration from argon to cobalt. Okay, so after argon, you go to 4s. There's two elements, so it's 4s2. Okay, and then I go 3, and on them 3d, and I count to cobalt. 1, 2, 3, 4, 5, 6, 7. 3d, 7. That's cobalt. Isn't that nice and short? Much, much, much easier to work with. Okay, let's do another example. Okay, let's do the element, let's do strontium, Sr. Okay, so if I want to do shorthand, I go up one row, go to the end, okay, krypton, I'll put Kr, square brackets, okay, and then that's what comes after Kr to get to strontium. Well, it looks like 5s, and strontium's here in the second position, 5s2. So much shorter. Okay, what you put here in brackets represents the entire electron configuration up to that point. Okay, so it's very, very, very short. Okay, and we do that a lot. Okay, in chemistry, simply because the longhand configuration is really difficult and challenging to write out. All right, the last thing is identifying a very special subset of all of the electrons for an element. These are called the valence electrons. Now these electrons are the ones in the outermost energy level. Okay, why do we care about the ones in the outermost energy level? These are the electrons that are used to bond atoms together. They're basically the ones on the outside, if you will. Okay? In our next unit, we're going to talk about how atoms are bonded to each other. And we're going to discover that it's the valence electrons that are responsible for actually doing the bonding. Okay? And what's key for them is how many valence electrons happen to be available. Okay, so one more thing you're going to put on your periodic table, and that is the number of valence electrons. Now it happens to be the same by family. Okay, this is the 1A column, also known as the alkali metals. they have one electron in the outermost energy level. See, they're all in position 1. Their last electron is in an s orbital and it's all by itself. These are in position 2. They have 2 electrons in the very outermost energy level, all of them. This entire family. Now this includes helium, okay, although helium is part of the noble gases. Now, we're going to skip the D block. They basically have 2 valence electrons, although as we'll see in our bonding unit, their behavior is very unusual, and they use some of the electrons that are not in the outermost energy level for bonding. Okay, now we're going to go to this group. I'm going to erase this down here. Okay, when we get to this column, the boron family, okay, it has 2 in the S and it has 1 in the P. This is the 3A family. They have 3 valence electrons. This family has 2S and 2 in the P. It has 4. This family has 5. You see the pattern? 6, 7, and 8. This is the number of electrons in the outermost energy level. Okay, so make sure you write that on your periodic table. How many valence electrons are in each of those for each of the families. Okay, we're going to skip the intertransition metals because we will not be working with them for bonding. Okay, so now that we know about valence electrons, we're going to do Lewis dot symbols. All they do is they show valence electrons for an element. Okay. We're going to put 1 dot for each valence electron. Okay, so if I do the element, okay, and so we're going to put 2 dots per side. So the minimum, the fewest valence electrons you can have is 1, and the largest you have is 8. So when I do a Lewis dot symbol, I write the symbol for the element. Okay, so if I do sodium, that's an energy level, that's in column number 1. I do 1 dot. Now I can do it on the top, the side, the bottom, but the point is it has 1 valence electron, so it has 1 dot. The next family is the alkali earth metal family. I'm going to choose magnesium as a member of that family. It has 2 dots. Now note that I have to put 1 dot on each side before I can put 2 dots. Okay, then we have aluminum is a member of the boron family. They're in family called 3A in the numbering system. That means they have 3 valence electrons. So I get 3 dots for the Lewis symbol. Okay, then we have the carbon family. It has 4 valence electrons. Okay, the next family, the nitrogen family, they have 5. Now, this is the first time I can get 2 dots on a side. 1, 2, 3, 4, 5. It's a lot of valence electrons. Okay, next family, oxygen family. Now we got 6. 1, 2, 3, 4. Now I can do pairs. 5, 6. Okay, notice the pattern. 2 pairs, 2 singles. Okay, the next family is the halogen family. I'm going to pick chlorine to represent that family. They have 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. Okay, and our very last family are the noble gases. They have 8 valence electrons, which is kind of a special number in the atomic world. And that's what Lewis dot symbols for the noble gases look like. Okay, so for any member of the family, the noble gas, the Lewis dot symbol pattern is the same. I would just write a different symbol. So if I wanted to do potassium instead of sodium, it still would be K with 1 dot, because the alkali metals have 1 valence electron. For the carbon family, if I chose silicon instead of carbon, okay, it would be Si with 1, 2, 3, 4 dots. So we just substitute the symbol for the element that we want. Okay, look at the family, how many valence electrons that whole family has, and we put the number of dots. And that's how we draw Lewis dot symbols. This is important that you be able to draw them correctly, that you know how many dots any element gets, because we're going to be using those, again, like little building blocks to build an entire molecule in our next unit.